So now, once you've gotten that, let's go over to, let's pull up our spreadsheets. And there, I thought we might go and look at these things here, but I decided we're only just going to look at the actual data that we have. And this stuff we're just not going to bother with. So I'll push it out of the way. So one thing right off the bat, I can put borders around it. So you select everything, you right mouse click, and you say, okay, I want all borders. And another thing we can do is we want these, and in fact, why don't we just select all of them, because we're going to be adding some stuff, and we want to make sure that they're numbers and that they have 2 decimal places. So it looks exactly like our lab, the data we were given. So the first thing we want to do, let's see what I can improve this a little bit. I have to always remember that I have this really big monitor. I try to keep everything on one side of the screen. So the first thing we want to get, oh yeah, so you can also, I typed in all these words, and when you first type it in, it looks something like this. And get rid of that. And it's pretty messy. So what you can do is you can make it bigger. I did that already for you. And this thing, these buttons up here, change where the alignment. So I'm putting them in the middle, left and right, middle, up and down, and then there's things called text wrapping. And now they come up nicely. That's why I had to make these cells bigger. Okay. And you can adjust the size. If you want to make them all equal, you select them and do something like that. In this case, I like to make this one a little smaller. And I make this one a little bigger, so I have some room over here. So first of all, let's calculate the average. So let's see, I have to get my tablet out of the way because it'll make things strange on the screen. So we start out by typing equals, and there's a bunch of built-in functions, but we know we want to average, so it gives us choices. Although you can't click on one of them to get the one you want, which is kind of dumb. So we just want a simple average. And then we select the items that we want to average, the data points. And then we close the parentheses and we get the average value. And now we want to get the sample standard deviation. And so we say equals. We start typing. We st. So we want st dev dot s, the sample standard deviation. Open the parentheses, and once again we select our data, and there we go. So I'll wait a minute, and if anybody would like me to repeat those, let me know. Repeat what I did, I meant. Sure. Okay, I was going too fast, huh? Can you see? The first of all, take a look at the final product. I double clicked on it, right? So then I'll do it over again. So anytime you want any kind of calculation, you always start with an equal sign. And what's nice about Excel is the functions are generally plain language. So I'm going to start typing in average. And then I just want a simple average. Okay. And then I select my first data. Now hold my left mouse button down. I may not have said that. Hold my left mouse button down. Select them all. See B7 to B21 now. And I close the parentheses first. Then I hit enter. And a similar process for the standard deviation. And let's see, I will just do that one over again. Equals S T and standardize. Nope. I see STDEV, and we want .s for sample standard deviation. Again, you're acknowledging that you don't know if you've done enough measurements to approximate the normal curve. And I select the data points once again. And there it is. So here's a neat trick. We can select those two guys. And I've put it into other videos. Now you see the little box in the lower right of the selection, and when I move my cursor over it, it changes. That little green box is called a fill handle. So I click down, hold my left mouse button down, and I drag it, and it fills them in. Now, of course, this one here, well, what it's actually doing is giving an error message because there's no values above it. So I can just select those two and hit the delete key. So now I've got the average and standard deviation for both of them. Does anybody want me to show that fill handle thing again? Oh, does that mean yes, Tess? Okay. All right. Oh, so that means you got it. All right, good. Limited bandwidth there. Okay. So, there's a Dr. Taylor here. He's been, believe it or not, he's retired, but he still teaches some classes. He was my advisor when I was at Cal State. If you can believe it, he's still here. And I was talking to him once about 2100 versus, say, 1100. And he told me that he likes to teach 1100 and 1200 better than 2100 and 2200, even though those other classes in principle have physics majors and engineers. Because you guys pay attention and you try really hard to do what I ask you to do. Whereas the other kids, like the engineering kids and stuff, I don't know why, but they don't actually put as much effort in as you guys do. Okay, so let's stop here for a moment and let's do let's think about this. So let's take these. I'm gonna take these numbers and I'm going to put them over here, and you can just sort of write them down into your notebooks. Oh, it didn't. And see, here's a mistake. I forgot to put some grid around this. And if I do that, then when I do a copy paste, it looks nicer over here. Here we go. So now let's think about this. So if we stopped here, we're saying, all right, we measure this one as 24.84 hours plus or minus 0.77 hours. And the same thing with here, 26.72 plus or minus 0.76 hours. Now, of course, we sort of know that that's not right. But if you say, well, let's take a look at this. If I take 25.84 and I add 0.77, 6, carry the 1, notice how, it's almost 26.72, but some of these numbers, I could take 26.72 and subtract 0.77, right? Because it does say plus or minus, 76. 6 from 12 is 6. 7 from 16 is 9. And then we're left with 25. Oh my goodness, huh? So now we have this situation like that, right? So we're seeing how the standard deviation of the sample shows you the variability of each measurement, and it's a measurement. It's a characterization of the spread of these guys. How much? If I say that the middle is 25.84. then how wide is the spread of them? And the standard deviation tells us that. Now the thing is, we can't really say that which one of these two populations is, if there's a difference between them, because their error bars overlap if we only use the sample standard deviation. But again, why do we bother averaging? And the reason we bother averaging is because we can now do the standard error on the mean. Standard error of the mean. Oops, so I went over, so I'm going to just make this bigger. And remember, that's the sample standard deviation divided by the square root of the number of measurements. So that's going to equal the sample standard deviation. Now you're going to love this one, and you may not have ever seen this command before. Well, you probably haven't seen standard deviation command either, but there's another great one. I divide it by square root SQ, see that? Square root, and then I open parentheses. Now I'm going to put a function inside of a function, count. This is really sweet because it tells you how many boxes you've selected. Now it may sound kind of dumb, but if you have hundreds of boxes or you're not even sure how many you have, this is a great command. And this thing is going to return, well, I'll show you in a moment. And I make sure I've closed all my parentheses properly. And just to show you, equals count. And there's 15 values. No, yeah, I picked, what I did, Tess, is one of the neat things about spreadsheets is that since I've already calculated this, oops, so let me do it again. I'll close it. Since I've already calculated the standard deviation in this cell here, B24, when I want to do the standard deviation divided by square root of n, all I do is I go equals, and then I just pick that box instead of typing in that whole equation again. Sweet. Yeah, you guys, I don't understand why the lab manuals, if you look at the intro of the lab manual, if you bought the whole thing, it says you're not allowed to use Excel. And I'm like, what the hell is that all about? I absolutely want you guys to get good at this. And Excel is, I used to be pretty down on Microsoft products, but I have this article I came across. Excel is actually a programming language, and it's a great way to do programming without having to learn a computer language. Okay, anyways, so now we want to get a square root. So SQRT, and we want the square root of the number of measurements. So we use this other function, count, whoops, open parentheses, select the boxes, whoops, and close that. The count, we close the count parentheses, we close the square root parentheses, and there's our standard mean of the error. You're welcome, Tess. And look, guys, don't be afraid. We'll get in person. Somehow I've gotten feedback from my students that some of their professors get mad when you ask questions. For God's sakes, you've got to ask questions. Because look, if there's somebody else in the room that has the same question, and you shouldn't feel like a dummy because the stuff's hard. Almost everything is hard the first time you learn it. I remember when I was working, I spent a lot of my professional life at Brookhaven National Laboratory on the East Coast, and and every Tuesday we'd have a tea, where we'd have coffee and tea and cookies, and it was just like get these workaholics out of their chairs. And I can remember, there was some world famous people there, and this one really world famous guy. He didn't win a Nobel Prize, but he should have, I think. Maurice Goldhaber. Everybody just called him Maurice. And I overheard him say once that everything is simple when you know the answer. So anytime a professor says to you, this is simple, they're not really being fair. Because, in fact, I learned this wasn't simple. Because when I tried to check my assumptions to get ready for this class, I realized that I had some things wrong. So now, how do we quote our measurement? So make sure you filled all this in. So I'll wait till everybody tells me they've gotten this table finished, and make sure then you save the file. Just realized I could do something here while I'm waiting a bit. Sure. That is this command count. I wanted to show you what count does. So I used the count command to tell me what was n, the number of measurements. Does it make sense yet? You're welcome. Yeah, I'll get that out of the way. You don't really need that. So I wanted to, where is it? Well, that's weird. Ah, here it is. Oops. So your logbook Whoops. Here's the Excel file. So somewhere in your logbook, hopefully you can print something. So ideally, you would just do something like this, copy, and print it. Oops. Here's something I forgot. Well, most likely you're not going to face this, but I'll just show you what I did wrong. I need to make a background on these. I got to make a white background. It doesn't even change what you see there. So you've already done your example calculations here, except you haven't done an example calculation of the standard error. So let's see now. So this probably, you wouldn't have this on the first page. So somewhere later on in the write-up, you've got this table, and let's say back here, you've shown the equations and you've shown how you calculated them, and then you say, well, look, here's the data points. I made an average, I made a sample standard deviation, and then the new one is this standard deviation of standard error of the mean. And let's see if this works. And so, okay, once again, well, actually, that's what it would look like if you wrote it in your book, right? And then you explain how this is and I'm going to show you more about what it means, but so you've already pretty much shown the equations, and then you've got the data table, and you say, we calculated the average just as on page so-and-so. We calculated the sample standard deviation that you can see over around this page. And then the new number we calculated is this so-called standard error of the mean. And this is how it's calculated. So notice, and I maybe should have been a little more specific, notice that it's the sigma x, and then, but it's got x with a little bar over it, and the bar means average, just like I have right here. Sure. Well, that's a good question. Thank you. It's sort of. I started out by going over the pre-lab just to make sure that you guys, it's always my practice to go over the pre-lab and make sure everybody has the correct answers. Because remember, when I have you do the pre-lab, I don't care if you get it right or wrong. I just want to see that you did something. So I always like to make sure that you understand what the pre-lab, the right answers are. So don't worry about having a particular order. You could put an entry in your logbook. Let's say that you did the pre-lab and you got it all right, and you were kind of dozing off while I was explaining it, right? So then you just leave your your logbook the way it is. But let's say, well, I think I added some new stuff, right? I explained this. I don't think anybody got that right. So now you just put in your like a heading, updated pre-lab or something like that, or updated background. Don't worry about getting things in a particular order, okay? I know that maybe the lab format document, a logbook format document makes you think you have to get it in a particular order, but in a real logbook, that never happens. But at the same time, it's good to like use highlighter and say, here, this is a pre-lab item, this is a background item, this is an analysis item. That way it makes my life easier. And again, the things that I try to set this up so that the work you do for me is things that you need to learn in your professional life. So keeping a good logbook, the goal of a good logbook is that you can pick it up. Not that I can pick it up and read it, that you can pick it up. I mean, I'm not that great at keeping a logbook. See, this is my personal journal. I carry it with me all the time. And the holy grail is that you can pick up your logbook next week or next month or next year and quickly understand what you were doing. Because let's say that if you're working in a hospital and somebody brings up a lawsuit against the hospital, and maybe you have a sort of responsible position, like I would advise people in health field to keep a personal journal. If they call you to the carpet, you can say, look, here's that date, this is what I was doing. But you want to make sure that it's understandable. So saying that what you've done the pre-lab and you've done other work and you go, oh shit, Dr. Harry gave us some other pre-lab info, don't sweat it. You just put it in chronological order and just put a little highlighter on. This is a pre-lab or background information. That's all. Okay. So now what we've done is I've given you a deeper background on these equations and why they're done the way they are, because the manual is not exactly correct. And the stuff you might look up, like in Wikipedia, is correct but needs different wording. So this is, you could call background, more background. And you've already done the sample calculations to demonstrate to the reader exactly what an average is and exactly what a standard deviation is, an example of it. And now we're in an analysis section. And in our analysis section, let's see what I want to do. I want to duplicate this. And let's get rid of this and this. And in our, oh, I just realized something. I'm just going to copy and, oh crap, come on. So now, we're going to say, now we're doing analysis. Now analysis, and you say, look, using the equations from previous pages, the average and standard sample, the sample standard deviation, we calculated those numbers for the full data sample for both the population A and population B. In addition, we calculated what's called the standard error of the mean, which is this equation. And the standard error of the mean is basically the sample standard deviation divided by the square root of the number of measurements. In fact, that is now, we already went over it a little bit, so you already have that equation written down. Now, let's take a look now. So now what we're going to do is we're going to quote not what we did a little while ago, but we're going to quote, oops, copy, paste. We're going to quote the two measurements as population A has a period. The period of population A is equal to 25.84 plus or minus 0.2 hours. And I suppose it should be 0.20, excuse me. And the period of population B is 26.72 plus or minus, turns out to be the same thing, 0.20 hours. Now what you see is there's no overlap. So we can definitely say that the two periods are not equal. And the simplest explanation is that if I add 0.2 to 25.84, I get 26.04. And if I subtract 0.02 from 0.2 from this one, I get 26.52, and there is no overlap. Oh, yeah, of course. Very good. Okay. Remember that we said before that sometimes this number is less, the A number is less than the B number, but occasionally we notice that an A number is greater than a B number. So remember our goal, or our hypothesis, so we're testing a hypothesis, and we're testing that the period of A is not equal to the period of B. And what that would tell us is that the nucleus, the nucleus, having no nucleus has an effect. And so since we have a bunch of numbers, we have no way of determining, of quoting an uncertainty, and we notice this sort of bounce. This is like sort of a bounce, like it's sort of vibrating a little bit, right? And sometimes when the two numbers are vibrating, they hit each other. That's a kind of an overlap, right? And in fact, they pass each other. So there's this region where the two numbers are equal to each other, or they actually switch in their being greater than or less than each other. How's that? Does that make sense? Right? Now, the sample standard deviation gives us a measurement of how much they overlap, and though the standard error is our gold standard, because we went to the trouble of averaging, and we want to understand why we bothered. And we bothered because it reduces our error on the mean. So now we notice they don't overlap. And how do we notice that? Well, we notice that because we said that they're each basically plus or minus 0.20, right? So I decided that since this is the smaller number, I'm going to add 2.2 to it. 0.20. Sure. Maybe I made a mistake. Okay. So, good question. I think I'm going to address it. So in this, for the A, since A, the average is less than B, I'm going to add the plus minus to it. But and this one's larger, so I'm going to subtract the 0.20 to 526. So did I clear up your confusion? You're welcome. And so we notice now that these two numbers are always going to be, this one is always going to be less than, because the two averages less than, these two extremes are less than. If I subtract, if you think about it, subtracting from the left number is just going to help us, right? 25.84 minus 0.20, 4, 6, 25.52. 0.264. And then if I add 26.72 plus 20, I'm going to get 2926. So it's still, so the average is less, the one extreme is less, and the other extreme is less. No overlap. How's that? So I did it a different way. So we can, right? Thanks, Tess. So that means that these two numbers are unique. They don't equal each other. Now, we don't know, we can't tell, all we know is that cutting off the nucleus makes a change. That's all we can conclude. But for sure, we can conclude it, that we can say with confidence that they're not equal. So I'll wait a minute and let you get this, write this down. So we're just about done. We have about another 10 minutes. Yes, and Tessa said she used to not like Excel. You know what? I really learned how to use Excel, and then they put that ribbon thing in. So again, showing you my age, and I just got so pissed off that I went to try Open Office and such. But you know, I just realized that Excel is, when you copy paste into other applications, you don't get errors, and you know, even though Open Office is free and there's lots of great people who work on it, you know, there's, when you pay for something, then you get much better tech support. I still hate the ribbon, but it's been around now 10 years or so. I'm finally learning how to get around it. Okay, so I'm going to move to the next slide. So if you want me to go back, just sing out. So we're going to do a little bit more central limit theorem. So that is a sigma. It's the standard deviation of this curve. So when I say 25.84 plus or minus the standard error of 0.20 hours, what I'm saying is that I may not know what is the true value, but I will tell you, I'm telling you that my 25.84 is 25.84 should be in this dark blue area. And if you see these numbers, 68.2% is 1 sigma. So I'm telling you there's a 68.2% that my measurement is 1 sigma of the standard error of the mean, 1 sigma away. So I've gotten that close. Now, a lot of times what people do is they quote a confidence level. So this is called a confidence level. And so in my world, we do usually just the plus minus, and that's the end of the day. And most of us, and especially in experimental high-energy physics, we deal with statistics all the time, so we understand exactly what it means. But the standard, you guys, especially in biology and chemistry, are going to probably face up to the 95% confidence level. So for the 95% confidence level, what you do is you quote 2 of the standard error on the mean. So if I say 25.84 plus or minus 0.4 hours, I'm saying that there's a 95% chance that this is the right value. or at least the right value is within 0.4 hours of that. And the reason is because of the central limit theorem, that Mother Nature somehow, all random processes are Gaussian, or they follow normal curves. It's just amazing to me how this can actually, and the way the mathematical proofs for these things are ridiculously hard to understand. Took me, I had to go, and I thought I understood them, but I spent the weekend relearning them. So we can do a little exercise and yell if you want me to go back. I want, yeah, let's just take this, copy and paste. So one of the gold standards of saying that TA is not equal to TB is that you want a 5 sigma difference. Now, a 5 sigma, that's what I forgot. A 5 sigma is like 99.999, I think, 6% confidence level. It's sick. It's really large. But let's take a look what we have here. Let's calculate the difference. 26.72 minus 25.84. So that is 4 from 12 is 8. 8 from 16 is 8. So the difference between them is 0.88. Now we need to say how many sigma. And that would be sigma of the mean, of course. Excuse me, I shouldn't write it that way. How many sigma of the mean? And the way you do that is you just take 0.88 and you divide it by 0.20 and you get something like 4.4 sigma. So that's pretty damn good, guys. It's not the gold standard of 5 sigma, but just these 15 measurements allowed us to say that we're at, and I forget how many, I think it's 99.99%. So 2 sigma was 95. So you see what happens is that each time you go another sigma, so 2 sigma is adding in, well, it's 95. Now, if I want to go to 3 sigma, I add in another 4.2. So 95 plus 4.2 is 99.2. That's 3 sigma. And we're saying that we're way out here. We're at about the 4 sigma level. So this is what statistical analysis is all about. And it's a statistical analysis when you have small samples, because we're not always able to take a large enough sample, but it all works because of the so-called central limit theorem. And you don't have to write up the central limit theorem in your book. What you need to do is write up that we calculated these numbers, we see that there's no overlap, and we're done. If you like, you could write up this business of well, you should write up about 1 sigma is to 68% confidence level, 2 sigma is to 95% confidence level, because again, this is something you may face in your professional lives. And just for fun, we calculated how many sigma differences, and we got so this is cool, right? Basically, we're kind of done. If somebody said, hey, we need a 5 sigma difference, then, oops, we'd have to go back and take some more measurements. And that's it. And so we won't go into any report because this is more like an exercise to learn about it. So I guess what I'll do is I could have you guys submit your spreadsheets. I'll make that. Um, nah, don't even bother. See, this is one of the reasons why it's tough to say what are the weights of pre-lab, lab day notebook, and final notebook. Oh well, there's right. So pre-lab day and final, right? It's always like because each lab is a different. Excuse me, that's wrong. That's report. This is logbook total. So it's always a juggling act. Each lab is a different amount of work. Yeah, wait, something. Oh, yeah. Um, this part here is actually we've done. This is the results when we talk about um, this. So this again is results. And sure. Oh no, no. I was thinking of doing a see these data there. If you notice that these data are exactly the same as this bit, but each set is bigger and bigger. And I was going to show you that the real value of these of A is 26 and the real value of B is 26.2. And I was going to go through this whole exercise to show you how we needed more and more numbers to show that because they're so close together. But I realized that it wasn't necessary. I think we got everything we needed out of just this bit here. So that's right. Don't even worry about those. Sure. Both ways. Both ways. Right. Because if I say 1 sigma, it's of course plus or minus, right? So if I say my measurement has an error of 1 sigma, and what that means is that I'm telling you that my 25.84 has a 68.2% chance of being the true value. We don't really know what the true value is, right? Generally speaking, we never know what the true value is. But see, this is the thing that people don't, that the lab manual and many books don't say properly. And then if we quote 2 sigma and being careful, it's this sigma, the standard error of the mean. If I quote 2 sigma, then I'm saying that my 25.84 plus or minus zero point 0.4 has a 95% chance. So we got 34.1, 34.1, 13.6, 13.6. That doesn't actually add up to 95, does it? 12. Yeah, 68.2. Yeah. Right. Most people just say 68%. And most people then say 2 sigma is, let's see, this is 68.2 plus 27.2. So that's 4. Yes, that's 95.4%. But usually people just say 95%. Good. I'm glad you're paying attention. Yeah. Good for you. Yep, yep. Yeah, that's the struggle here, Tess. I got to try to give everybody a tidbit. That's why sometimes I say, look, if you don't understand this, don't worry about writing it down. The big deal that I want you to understand is for everybody in the class, what I want you to understand is that you use statistical methods when either you don't know what the uncertainty of each measurement is, or you have no way of knowing, or you just can't get a good handle on it. And then once you use the bunch of numbers, the average is this, the sample standard deviation is that, means this is what the sample standard deviation means, and this is what the standard error is. And at the end of the day, the thing that you report to the outside world is the average value plus or minus the standard error of the mean. And if everybody in the class walked out of here with that much, I'd be happy. So things like 68.2% confidence and 95% confidence might be a little heavy for some people in the classroom, and it's no big deal if you don't get that. But some of us are, if we're going to do chemistry or bio research or even medical research, you're going to have to understand what 95% confidence level means. Good question. Do you remember, Tess? Yeah. Oh, yeah. She asked me where did I get 68 when I see 34%? So she asked me, is it, yeah, right? Because it can swing both ways. Right. Good. All right. Any other questions? So great. I'm glad. So what I see in the future is that, in principle, we try to go over stuff like this in class, but we can also do it via Zoom as well. And we'll just have to see how it goes. But what at any given time, I try to provide with each lab, each module on the home page would be like what you should have in your logbook, and I try like a list of things that should be in the logbook, and I've sort of gone over it in real time. And then if we have a report, I try to actually write you up a little outline of, let's see if I have an example. If you need to go, just go. I'm going to just see if I can find an example for you. Yeah, I did it for the 1200 lab people. Here we go. So, let's see. Analysis notes. Yeah, I think. Oops. Nope, those are just screenshots. Oh well, I'll when the time comes. But I got in the habit of giving. Here we go. So my goal is for every lab to give the students a list of things that should be in their reports and what should be in their logbooks. Well, this isn't a good one, but I have better ones. But anyways, that's my goal. In worst case, I'll just tell you in words, or I'll write notes to you. Okay, I'm tired. I didn't think we'd go this long, but you guys seemed like you were soaking it up, so I got into it. So if there are you're welcome, Marco. So if there's no other questions, I'm going to close the session, and I've been recording locally. Lorenzo, you're welcome, and who else was there? Yeah, Tess. And I'll get that posted up as soon as possible. And remember that you can download these slides. If you like, I'll make this version with my scribbles on it too. I can post that as well. Okay? So I'll get the next week's lab stuff posted as soon as I can. And in principle, look at me. I can stand up. It's a little painful to walk around, but next week we should all be together in the lab room in bio. So I should be there next week. I'll confirm it. Well, you'll see. I won't know really, I guess, till Sunday. So I'll see you all soon. Yeah, sure. If you can. If you can't, just handwrite. You can handwrite in this isn't so big. At least handwrite in the bottom part here, where you say the final average and such, this sort of stuff, at least, okay? You're welcome. Okay, very good. See you guys. Yep, Tess. I will. I'm gonna relax now. I'm tired. I worked really hard on this. See you all soon. All right. Okay, close. Oh, I gotta turn off the recording too. Here we go. Yep.